Okay, good morning everybody. I think it's time to start, and for people over the YouTube channels, time to wake up. So welcome to the Ellis wrap-up conference and Ellis community event. And now for those who haven't heard about Ellis, that's actually a good thing if you haven't and everything has worked, because when we started, that's exactly what we said will be our main KPI or main success measure. So those who are playing piano and have started as kids probably know what Für Ellis is. And now what Ellis is, it's a network of excellence, network of European excellence centers, which was started as a result of an EU call. A bunch of people in the Ellis community got together to write up a grant, got it, for the purpose of bootstrapping the activities, many of the activities that the Ellis Society is then running, and at the same time, the Ellis is the exit plan for this EU project, which is ending in the end of August. Initially, the idea was to have more of these kinds of community events, but then, of course, the pandemic hit and we had to change the plans, and people's practices of going to the conference changed it. That's why this is actually the first and last really large community event that we have managed to pull off, but there has been many other events. Okay, I have been asked to tell a few practicalities about this conference. First of all, we have, of course, several parallel sessions by Ellis and the research programs, and 3 keynotes. I'm sure you all have the program. So a few practicalities. Some of the sessions are in the room called Eliel, which is named aptly. Many of these Ellis-driven EU projects start with L. So it's across the street in the hotel. Then you go outside from this building, just go straight ahead and you'll find it. We have several parallel sessions. They are all open, but the organizers have a minor wish that please attend the session. If you have been nominated to a session, please attend that if you can, because we have some capacity limitations in some of the rooms. Because you feel free to try something else. Boat cruise this evening. So your badge is the ticket if there is a small boat in the corner. If somebody who would want to go doesn't have one, I can borrow my badge. I'm not sure if I can join. So unfortunately, Ellis was not able to cover all participants of all the workshops, which would have been too much. Sorry about that, if you would like to go. I hope the workshops are organizing stuff themselves. This is how I understood things. Now, because this is the wrap-up event of Ellis and this is being broadcasted, I think I need to say some things about what we should remember the Ellis for. So it has and has a joint mission with Ellis in making Europe more attractive for existing and upcoming talent in AI, especially machine learning. And by numbers, attracting the numbers of fellows, really outstanding fellows and outstandingly promising younger people has been successful. Maybe if I need to single out one really big achievement, and now remember this is of course a facilitatory action, of course the real highlights are in the research, but this is what the Ellis did and which wouldn't have happened without the Ellis support, is the PhD program. And this is really amazing. So all kudos to the people who run this, run in the beginning and now with the new team is running this. So the both the number and quality of the applicants is really outstanding, and then the PhD program is making sure that they get good opportunities in Europe. Research program workshops, winter schools, summer schools, there's plenty, there is 3 today. Compute, ultra important for both Europe and our community. There have been several contributions to that. I'm not going to read all of them. The last one I want to mention, there has been really salient people given advice to the European Commission, the European community. If I again single out one specific thing, I think it is the strategic research agenda here, which I am sure has been listened to in the Commission as well. So now we have too many people to thank, so I'll mainly give kind of joint thanks to everybody, but I need to mention maybe 3 people. One would be Arnold Smulders, who was my co-director in the beginning. We started this together, and who is here by a vote, actually. Thanks for coming. The other person without whom I think we wouldn't have this is Sami Heinesmäki, who is sitting over there, grant writer from Aalto, and the proposal was that good only because of Sami, and who's run much of the coordination business in the beginning. Petri Myllymäki, who has been the vice director, is sitting over there, and then Chris Murray and Petri are to thank for this conference. I should mention all the work package leaders and coordinators, but I don't think we have time. We want to start listening to Bernhard's talk. So I just propose that let's give a big hand jointly to everybody who has contributed. And now I think it is time to switch to the first keynote. Bernhard Schölkopf here certainly does not need introductions, but I'll just mention the two of the really important things. He's the chairman of the board of Ellis and runs the first Ellis Institute that there exists. And of course, from research, we all know him, so I'm not introducing him by research. Bernhard, take over.
Thank you very much, Sami. All right, so very happy to be here, and it's the end of maybe the first chapter of Ellis. And if I think back, we've come a long way, and I have a few slides to, I don't know, maybe tell you a little bit about this story and how it unfolded. But I have sneakily used a title for the talk, which leaves it open to interpretation whether it should also cover something about science in the end. I mean, we've spent a lot of more time than we were wishing for talking to politicians, etc. But in the end, our motivation to do this was science. So I thought it maybe also fits to have a few scientific slides on this talk. So I'm going to talk a bit about Ellis and then about 2 areas that I think are promising and important for research in AI, maybe not just European AI. So let's start with a slide that I've often used to sort of get us thinking about the big picture. So this is a picture from around the time of the first Industrial Revolution by the British painter Ellis. You can see lots of chimneys developing. You don't yet see cars, which my wife says, which is why this picture looks so peaceful. So there's lots of pedestrians here. And our current revolution has been likened to industrial revolutions. And if we think about the first 2 industrial revolutions, maybe to understand our current situation, it's clear that they were both about energy. So the first one with steam power, water power, etc. And then the second one came with electrification. So in the second one, an additional energy form entered the stage. But it's all about converting and processing energy. And similarly, one could argue that the current revolution is all about processing information, which is of course closer to what we call intelligence. So at the beginning, it was processing information using programs written by humans. So that's started in the mid 20th century, and now increasingly processing information that's automatically extracted from observations using machine learning. So there's probably also multiple stages, and maybe we don't yet understand information as well as we now understand energy, but that was the same with the notion of energy. The notion of conservation of energy wasn't so clear in the history of science, certainly not from the start. And also the notion of conservation of information is maybe not so clear yet, but I think we will get there. So it's clear that in the first industrial revolutions, they had big consequences, not just for science and technology, but also for societies. And we're beginning to see some of these consequences also for the ongoing revolution. And history shows, of course, that information can be manipulated to help control people. And we see that this is the same nowadays. We have additional means. We can generate fake images that have never existed. So the means for exploiting these tools or the means for misinformations have become much, much more powerful than they have been in the past. So we can do these things now at industrial scale. So clearly we expect that there will be major consequences of this ongoing revolution, and maybe they are even in a sense more major because information is much closer to what makes us human. So it's closer to the human condition. We think we are very good at information processing, much more so than we think we are good at energy processing, we as individuals. So this revolution touches us much more closer to the core than the previous one. And there are all these discussions. I'm not going to go into them. We've also tried to add a European voice. These discussions, they tend to be dominated by American voices. We've tried to add a European perspective to this, and we also invite all the community to play a role in this. I think it's important that we also have a voice in these kinds of discussions, which are often driven also by economic interests and by media hype. Anyway, let's go back 6 years. So 6 years ago, many of us published an open letter, which was entitled Initiative to Establish a European Lab for Learning and Intelligent Systems. So we had been discussing about this for maybe the year before. We were wondering, what should we call it? Should we use the term AI? Should we use the term machine learning? In the end, we said, okay, let's call it intelligent systems. And in this letter, we were asking for a number of things, and we thought this is so compelling. It's so clear that Europe has to do this. They will just directly ask us for our bank account number and tell us to get going. So it didn't quite work like that. Politics is much more complicated, and a lot of people here in the room helped us navigate this. What was the basic idea? So we said for Europe to play a role in these ongoing changes and to push them in the right direction, we need a plan that has as its core component the idea to attract and enable the best talent on all levels, including on the level of PhD students especially. We heard about that already. We think in order to attract and enable these talents, we need to create regional ecosystems. It's not about just having one lab, but we really have to do something that works with the strong ecosystems in Europe. And then we have to connect those to best benefit from the overall strength of Europe and make attractive offers for students who want to spend time in multiple ecosystems, etc. So in the same year, we had a very spontaneous but still very successful founding ceremony. This is a picture taken early in the morning in a cafe in Montreal. Europe's was in Montreal. All the Europeans were awake early due to their jet lag, so we went to this place basically at the time when it opened. And this is actually a cafe. So in this cafe we had some coffee, and then we basically founded Ellis. And I think we can see Sammy here in the background, and was pointed out to me that almost everybody is smiling, but Sammy is not smiling. And and so somehow, and it maybe he didn't yet know that he's going to run Elise. But maybe he had some kind of premonition that this is going to be more work than we think. So it's easy to found something, but then the hard bit is actually to follow up and do things. I see Arnold also smiling about this. Yeah. So this was followed by various meetings. Here's a meeting with the Prime Minister of Baden-Württemberg, who then also gave us significant money to get things started. Then the next step was we were very much inspired by the Canadians, the CFAR program on learning machines and brains, which at the time was run by Jan and Joshua. And they, especially Joshua, then helped us evaluate the first Ellis programs. So, and this is the set of first Ellis programs that we then started. And after that, we thought, well, we have to get closer to institutes. We're asking for a network of institutes. So how are we going to do that? And we said, well, let's try to start with an intermediate stage. And, it's funny, sometimes you remember the phone conferences, you remember where you were when you had these conferences. In this one, I remember I was in Chile because I wanted to see the solar eclipse, which was taking place around that time. In 2019, I don't know, May or June or something like that. And I had to stop somewhere I was in the Atacama Desert, and there was not much Wi-Fi, not much phone coverage. I had to stop on a parking spot where it looked like I can dial in, and then we discussed about the Ellis units, and we said let's do this as an intermediate step to institutes. So some people were saying, well, we are asking for institutes. If we now start units, how are we ever going to get to institutes? But then the other argument was, well, we have to use the momentum. We have to establish a credible path. So I think there was also a worry, how many people are going to want to start a unit? Anyway, so we made the open call, and then surprisingly, we got 28 proposals. We never expected that. And this led to a very strong set of initial units, including many of the top places in Europe. And people all volunteered to contribute their own money to the network. So there was no outside money going into that, which was quite amazing. And then Elise, so Elise, what should I say about it? I think for Elise, I also remember one of the play. I remember that we had there was this ongoing discussion, should we do it together with another AI initiative, or should we do our own thing? And the others already had set up everything, and they had a credible plan with a coordinator, and we didn't really have that. We just had the idea that we would like to do it somewhat differently, built around modern AI and machine learning with top people. And then we were struggling to think about who could do it. And I remember also a phone call, again, the place. I was somewhere in the security control of an airport, and I like to think it was in Asia. And I think Arnold and Sami were there, and somehow we managed to convince them to lead this at the beginning. And so a proposal was put together. There was not much time. It was written fast. Relatively fast, but it still got the top score in this reviewing process. That was a great encouragement. Reviewers loved it, and it was funded. And then there's a picture that Daniela found for me for my talk. She says this was the Ellis board meeting where Sami and Petri joined, and we congratulate them for the Ellis success. And according to Daniela's notes, Sami said, I am not sure it's something to be happy about. Not sure yet, yes, not sure yet. Okay, and then we launched the Ellis PhD program. So this, I think, wouldn't have happened without Elise. We hired a great team of initial people. Daniel is still with us as our web admin. Daniel is actually going to be, is just about to start. He's going to be employee number 1 of the Ellis Society, so the first person actually paid by the Ellis Society. So he's in charge of the web page and especially the PhD program. So this is where your unit membership fees go. They are paying for Daniel, and they will probably also pay for more people, but we're being very frugal. So we have our headquarters in Swabia in Germany, which is known to be the tightest place after Scotland. So hopefully we may make good use of that money. So Ellis continues to get more visibility, more impact. This was a memorable event with Margrethe Vestager, the Vice President of the European Commission. I remember the date because it was my birthday, and it was a lot of work to prepare this, but then afterwards. She's a very friendly lady, and as a reward for sacrificing the birthday, she was singing "Happy Birthday" during the press conference. So we had various meetings with Angela Merkel, and here's a meeting with the Royal Society, and I think CNIS and Max Planck Society. We're starting to run various workshops and events. So this was the first so-called unconference, which was a lot of fun. This is the second one, which was run in Paris last summer. Starting to win prizes. Here we have Nuria, very proud with the prize in hand. We were starting to engage more with the European Commission. The next call came out, and again we said we have to put together a proposal. This was ELSA, so you see a theme emerging in the names of the proposals. Last night we were discussing this, and thankfully there are lots of names that start with EL. So that was maybe a coincidence, but a nice one. So ELSA is studying security and its connections to machine learning. More event highlights. I think this is the doctoral symposium. We had a very nice event where we were teaming up with the Lion Initiative that's working on open source and foundation models, with a panel discussion that also involved members of OpenAI and members of the European Commission. We had, and then the next project proposal came around, Ellis, which again passed the reviews with flying colors. I think this is a picture from the first Ellis meeting. I think these are already you saw on one of the slides of Sami. So people started to really look to Ellis when it comes to policy advice. Serge Milonji, one of our board members, he always says it's important. I think he's quoting Henry Kissinger, who do you call if you want to call Europe? He said it's important that people feel if they want to talk to European AI, they talk to Ellis. So I think we're getting there because most of the top people are now in one way or another linked to Ellis. So we think that's great. Also, the German AI strategy then started taking Ellis really seriously and declared publicly that they want to establish Ellis as a European and international networking platform for young AI researchers. So I think especially the PhD program by now is so successful that nobody can ignore it anymore. It's probably the most attractive PhD program, clearly in Europe, and one of the most attractive in the world. It's quite unique. I think nothing quite like this exists. And we're actually about to make it even more attractive, which I cannot yet announce, but stay tuned, it will come soon. So, so we also, I mentioned we started to also have discussions, or we started to contribute to the public discussion. So sometimes we want to do this sparingly, sometimes we put out statements. We always try to carefully word them because we know that Ellis has a diversity of opinions. We just want to make sure that the overall discussion also represents views that are represented in Europe. We contributed to the discussion about the need for computing resources. This also led to a joint statement with several EU-funded networks. We had statements on open source. And maybe here, just as a set of milestones, so we've come a long way, six years. I think I mentioned many of these things, so where do we stand now? So with Ellis, we added 2 more research programs, 6 new units. We now have the first Ellis Institute in Tübingen. I think I have a picture about that. In the PhD program, just in this season, we had 3,000 applications. We have a partnership now with the Oberwolfach Institute in Germany, which is a top place for mathematics or for mathematical workshops. So Ellis programs can run workshops in Oberwolfach. And and we are close to signing agreements with 2 more further outstanding partners in Canada and Europe. So it's great. This is a picture from last week where we had the opening of the first Ellis Institute in Tübingen. You can see there's a button here, and people are for some reason believing that if they press this button, then magically something will happen. So, and this button I think will appear later in my talk again, maybe. Yeah, and so this is the president of the Max Planck Society, my current boss. This is my former boss when I was a PhD student. Well, I was in a lab that he was heading. He was not my PhD advisor, but at Bell Labs he was the department head at that point. At the end of my PhD, and this is the Baden-Württemberg science minister. So today, where do we stand? Just a few pictures. I think you see many of them here in the room. Maybe we can also briefly introduce them if you want to talk to them. So Serge is sitting over here. Nicolo, raise your hand. Florence is also here. Anada, I've also seen. Yes. Neil. I'm checking if they all attend my talk, yes. And Nuria, I think Nuria is around, but she's also organizing something. Okay. And I think Josef is on vacation, very much deserved, and I think Seb maybe also. Yeah. Okay, so this is the current state of the PhD program. I've already talked about that. It's really great. We have maybe the one news that not everybody knows yet is we now have a 3rd track. So we had the academic track, the industry track, where you co-advise with an industry person. And now there's an interdisciplinary track. It's motivated by the idea that really AI and machine learning is starting to have a large impact in the sciences. And we want to be able to have PhD projects that are co-supervised by a core Ellis person and a person from an application area. And normally we have pretty high standards as to who qualifies for a supervisor. And of course, if someone works in microbiology, they don't publish it in Europe. So we want to be able to have this kind of projects also if they're co-advised by top people from other areas. So I think, well, we think this is going to be also attractive. We have more research programs now, so we are trying to, whenever we have a new EU proposal that is sort of instigated or supported by Ellis, we ask them that they also put something in the proposal that adds to the network. So they sort of help strengthen the PhD program, start additional research programs, etc. So this is working very well. We now, and actually I think this is maybe not, I think it might be 41 now. I believe we have 41 because Warsaw is not yet on this map. And also we have an associated unit in Lviv in the Ukraine. So the network continues to grow. There's a discussion as to how fast we want to grow. Do we want to get to a stage where maybe some countries have 10 Ellis units, or do we want to tell them, look, can you start clustering them and working together more closely? Because we never wanted to play the numbers game. We wanted to have excellent places. But actually, surprisingly, there's quite a few really strong places across Europe. So we're trying to balance this. And I think we're also planning a meeting during ICML with the different Ellis unit directors where we want to have this basic discussion as to how we continue to grow and how do we allow for excellent new units to come in, and how do we continue to motivate the existing ones, etc., to also build the network. We have also painfully built new organizational structures. We noticed things where at the beginning, basically everything in Ellis could be done in a small room around one table. But it was just getting too much work, and we wanted to become a bit more professional with the structure. And this is still ongoing work, but this is what we've established last year. And it's we're beginning to see the benefits of this. So we have the board, which is now more doing strategic things and trying to do less day-to-day work. We have the chief of staff, Daniela, who is also here over there. We have one board member, and that's currently Serge Belongi. I think at the beginning it was maybe Nuria, which is also part of this structure here, which is called the Executive Committee, that also meets weekly. And we have a COO who is actually doing this voluntarily, pro bono. He's an employee of IBM, and he's a person who Nuria has known for a long time, with a lot of management experience, who's supporting us in these kind of decisions. And then the executive committee oversees different areas that cover the different fields that Ellis engages in, and it's in charge of all the operational things. So that's the current structure, and I should say, as with everything in Ellis, if you have positive feelings towards Ellis and you want to contribute, I think there should always be a way to contribute here, because Ellis is really built and run by volunteers. So we're always keen on getting great volunteers in. And it's a little bit of work, but I should say also, I mean, last night we had a dinner with the board and with our Finnish friends here. It's also a lot of fun because it's a nice group of people. So I think none of us really would say this was a waste of time. I think we all enjoy it, yeah, because there's a strong camaraderie and it's also fun, yeah. Okay, so more recent activities we had across Europe, in Europe's parties. Where sort of maybe as part of this effort to reduce the carbon footprint and delocalize these huge conferences. I mean, who wants to go to a 10,000-person conference? We started doing decentral events, and for instance, we had a nice one. I only know the one in Tübingen where I went to. It was great. Basically, I mean, there's so much interesting work going on in all these different ecosystems, and it's even hard to keep up what's going on in your own ecosystem sometimes. So this was also a very nice thing, and pretty much self-organized. So that's the great thing, if you don't have to centrally push these things, but they just magically happen. We've become a founding member of the International Computation and AI Network. That's an initiative driven by the Foreign Ministry of Switzerland to provide compute power also to places that normally would not have access to compute power. We had a Future of AI in Europe workshop in Brussels, organized by the German Ministry of Science together with the French Ministry. What's next here? We have, I mentioned our partnership with the Oberolfach Institute. So these are 3 Ellis workshops that have taken place there. PhD program, I think you will hear more about this anyway. It's amazing if you just look at the events just from the PhD program. It's very, very impressive. And I think my impression when I talk to my students, it's by now it's very attractive to be part of the Ellis PhD program. So most students really want to be part of that. So we've come a long way. We are currently thinking about the next EU grant. You might have heard there's a large call, 50 million euro for in the area of multimodal foundation models. Again, we're trying to put together the strongest possible team, or maybe teams. That's currently in discussion. There we had an information session or a discussion session recently, and these discussions are continuing. So, so much about the Ellis structure. So I mentioned already in the title, I put this in parentheses. So now I want to talk a little bit about open problems of AI as I view them, or of course very much colored by my personal interests. And I want to focus on 2 areas. One is AI for science, which is something that I've been interested in probably for the last 20 years or so. Because when I got my first job at Max Planck, I was in a biological institute on a biological campus, and it was wonderful to start collaborate with people from all these different areas. And then afterwards, I want to give you a few thoughts a few of my thoughts on the future of representation learning. So, I feel like I'm gradually waking up. I'm jet lagged. This is 1 hour ahead of my time zone. And I was only finishing the slides last night. So I'm sorry if I've been sucking your energy so far, but I feel like no, we're talking about science and hopefully we'll get better. So this is a project that I'm really excited about, that we've been working on for the last few years, and this is about gravitational wave inference. So here you see a video, and this is a video of a certain binary black hole merger, GW150914. This was the first event that was detected, and the video depicts how it would have looked for a nearby observer. So you don't see black holes, but of course you see, maybe I'll play again, you see that there's an area where you don't see anything, so light cannot go out. And then around you see these strange distortions of the background field, which are basically distortions of space-time itself. And you see these two black holes orbiting each other, getting faster and faster, and at the end, I mean, they are orbiting each other, I don't know, let's say 100 times per second or something like this. So you have to imagine this situation. You have two things, both of them heavier than the sun, and they're orbiting at a frequency of hundreds of hertz. And then at some point they are so close that they merge and become one black hole. And this first event, they measured it during, it was not yet an official observation run. They were still sort of working and calibrating the instrument, but already recording data. And then at some point suddenly there was a postdoc or a student at night saying, well, I've measured something pretty strange here. And they found this first event, and they figured out afterwards the event was so loud in the sense of the amount of energy, they could have measured it no matter where in the universe it would have taken place. It was not, it was pretty far away, but it could have been even much further away. And so what you measure then is these length distortions of these kind of instruments. They measure length changes across a distance of a few kilometers. The length changes are tiny, so you have to imagine this is a wave of space-time distortion that travels through everything, in particular through Earth, and then you measure a distortion which is like the fraction of the size of the nucleus of an atom. So it's tiny, and you get these curves here. And of course, they're very noisy, and you have to be careful about even the faintest 50 hertz oscillations, etc. And then from these things, you try to measure what were the physical parameters of the black holes that just merged. And what you do have is you have a reasonable forward model, so you can run simulations at different levels of accuracy. Usually you don't really solve the full field equations. That's much too expensive, but you have simpler equations that you simulate, and then you run the simulation, you generate waveforms, and then afterwards, traditionally they've sort of fitted these, they run some search trying to fit these waveforms to whatever you've observed. So basically what we did is we train a machine learning model to directly do this backward inference step and to directly produce a posterior distribution of the physical parameters given these waveforms. And there's a reasonably small number of physical parameters, since black holes don't have a lot of parameters. There's this thing called the no-hair theorem. Black holes don't have hair, so a black hole is fully, if it's in equilibrium, it's fully characterized by its mass, its angular momentum, and the charge. Now, charge you can ignore on a cosmological scale. So basically, each of these black holes has an angular momentum and a mass, and of course, then they have certain positions in the sky. So there's 10 or 20 parameters, and you want to estimate the posterior distribution over these parameters. And in the first work, we did this using normalizing flows, and it works extremely well and extremely fast. And we are now we're just finalizing a paper where we do the same thing also for binary neutron star mergers. So a neutron star is basically something that wasn't quite heavy enough to form a black hole. So light can still leave it. But if two neutron stars merge with each other, they can be heavy enough for a black hole. But these are particularly interesting events. And it looks like we can even measure it. We can even estimate this already, let's say 10 seconds before it takes place. Which is great because then you can point optical telescopes at this thing and measure in the optical spectrum. So this has been a lot of fun working on this. Oh, okay, could have showed you the video in large. So here's another example. Collaborations with physicists. This was also a lot of fun, and we're actually now starting to continue in this direction. So this was the idea was you have lots of images of astronomical objects on the web because there's lots of amateur astronomers and astrophotographers, and you would like to use them scientifically, but it's hard to do so because they process their data often in ways that are not fully, well, almost always in ways that are not fully specified, so making it hard to use it scientifically. So you have all these images. This is results of an image search for NGC 5907. So NGC is New General Catalog. It's a catalog of deep sky objects. This is a certain galaxy, and then you get all these images. And let's say you don't know how they were processed, so it's hard to combine them and to get any information out. But let's assume that people processed them in a way which is monotonic, which means that whatever is brighter after processing, so if there's a certain brightness relationship between two pixels after processing, it should be indicative that the same relationship was true before. So otherwise it gets hard. So the brightness ranks should be robust under processing. And then we basically, we automatically register all these images. It's a process called astrometry. So there's a beautiful method which was developed by the late Sam Roweiss together with David Hogg. And then, so we register all these images, and then we use the brightness relationships to form a consensus image. So this is now related to voting theory and voting aggregation. Basically, each image gives us a partial set of votes as to which pixel is brighter than another pixel. And then we can produce an all-sky image. Each of these images, of course, doesn't cover the whole sky, but it gives us partial brightness relationships, rank relationships. And we try to find a consensus. And so this is now for that galaxy. We see how gradually these are the new images coming in as they're registered, and then gradually a consensus image emerges, and consensus image in if you afterwards you do a tone mapping, then starts looking like this. Now this is interesting because you see a certain structure emerging over here, and if we look at this structure, so this was all from amateur images, we can compare it, and this is the reason why we looked at NGC 5907. If you compare it to the deepest professional image, you can see that this structure here also appears on this deepest professional image. And that's a tidal stream. It's a leftover from a galaxy having collided with another galaxy. So it's very interesting. We didn't get this part up here, which we were slightly confused about because it looks like it should be as bright as the part down here. Anyway, we published it. But then, interestingly, a few years later, a controversy emerged among the professional astronomers because several other professionals also could not reproduce this part up here. So that was nice to see afterwards that our method, which is based on this chaotic raw data, found something scientifically interesting. So here's another thing. This is now more closely related to causality, a topic close to my heart. This is an application in looking for exoplanets, and I apologize if you've seen it already. I've used it in a number of talks, but I'll make it brief. So there was this satellite, the Kepler Space Telescope, which was orbiting Sun, or is still orbiting, it's not working anymore, and it was taking pictures of a certain area of the Milky Way for several years. And it was doing so in search of exoplanet transits. So an exoplanet transit means you have a star that's far away, which has an exoplanet that periodically partially occludes the star. Now, planets tend to be much smaller than stars, so partially might mean just 1%, or it might mean even much less than 1%. So you get a tiny dip in the brightness of the observed system, because these things tend to be so far away that you cannot see the planets directly. And of course, you can only see this thing if the geometry aligns and you look at it from the side. But Kepler was looking at several hundred thousand stars at the same time, so geometrically there should be quite a few cases where this does align. So for instance, if you were to fly out into space and assume uniform distribution over the sphere, and you look at our own solar system and you are asking, will you be able to observe a transit of Earth across Sun? I think the probability is something like 0.5% geometrically. So anyway, so we're looking for these transits, and from a causal point of view, the things that we measure, so these are now light curves. Each light curve is for a different pixels. These are adjacent pixels on the sensor. Each light curve is over 3 months. We measure these light curves, and the light curves causally are influenced, of course, by the astrophysical system. So that's the star and the planet out in space, and by the instrument itself. And the effect of the instrument is quite significant because it's a very difficult task, and we're looking for tiny signals. So, for instance, the instrument so the instrument is orbiting Sun, and it's always looking at the same direction. So its geometry with respect to the Sun is changing, which means that the solar radiation pressure is changing, and the instrument is trying to compensate for that. But nevertheless, the signal sort of moves around across the pixels a little bit. And this is what we can see here. Some of the pixels seem to get sort of systematically darker, which probably means that the image of the star is moving a little bit away. And other pixels that should belong to the same star are getting brighter. And what's interesting now is, as I said, we are observing several 100,000 at the same time. If we now look at the other pixels, of other stars, so stars that causally have nothing to do with our star here, then we sometimes see very similar relationships or similar behavior. And anything that is similar between here and here can only be explained by the instrument. So this is now the idea is now to remove this effect of the instrument, and we developed a method that is basically just doing regression estimation based on a suitably chosen set of inputs. So you choose a set of inputs of which you know it causally has nothing to do with our target, and whatever we can nevertheless explain of the target, we then remove. Sort of remove could mean different things depending on what's the model of how the influence is. If the influence is additive, then removing just means subtracting. It's actually more of a multiplicative thing, but let's not go into that kind of detail. And we have some theoretical results also for recovery in different settings. Basic idea, so we call the method half-sibling regression. And at the time when I was working on the paper, I was in England, and in England they have this thing. So, you know, there's this idea, or maybe statistics, that a certain fraction of all children has a father different from who they think their father is. And in some countries it seems to be up to 20%. And in England, then the suspect, the prime suspect, is the milkman, or it used to be the milkman. So we call this a milkman problem. And please don't take it too seriously. I don't want to offend anyone. Now, the milkman problem is not to determine which of the many children here is the milkman's, but the milkman problem is to reconstruct reconstruct the face of the milkman from the faces of all the siblings without knowing the mother. So it's based on very limited information, and the idea is for each of the kids, we try to explain the appearance in terms of the other children, and then the residual is basically our estimate of the milkman. Anyway, so we did this and built a lot of things around it together with a bunch of astronomers, and we found around 20 exoplanets using this, or suspected exoplanets. Most of them were actually we found 36, but I think around 20 of them were confirmed afterwards using other measurements or other methods. One of them was particularly interesting. It's called K2-18b. K2 means Kepler-2, the second Kepler mission. And it was interesting because it was potentially in the potentially habitable zone. So this means the zone around its host star which allows for liquid water to exist. So not too cold, not too warm. And then a few years later, I first didn't notice, but then the astronomer from New York told me there was on the news, I had read the news, but then he told me this is actually one of ours. So there was on the news that for the first time they had found water vapor on a potentially habitable planet using methods of spectroscopy. So that I had read about, and he said, well, actually, this is one of our planets. So that was a great coincidence, and there was a lot of discussion as to whether this could be habitable or not. But it was a very nice thing. And actually, it's interesting, just a few weeks ago, there was a exoplanet conference, and people are still discussing this planet. And the interesting thing is now is this debate about whether K2-18b might be what they now start to call a Hycean planet. So Hycean means it has a hydrogen atmosphere, so HY, and Cean comes from ocean, so it's a hydrogen atmosphere and an ocean, and probably the whole planet, if it's a Hycean planet, the whole planet will be covered by an ocean, and above it a hydrogen-rich atmosphere. And that's very interesting because this might actually be a good place for life, some form of life to develop. And apparently, so another person I didn't go to the conference, so someone told me the discussion now is whether it's in which way the atmosphere is mixing. So it could be, there's this effect that water and oil don't mix, but water and alcohol do mix. And they don't know whether this is something that the astronomers, they have nice terms sometimes. So they are now discussing whether it's a vodka world, which means that the atmosphere is nicely mixed or not. Yeah. And the conclusion is that more research is needed. So that's why we're all here. So this is all I want to say about astronomy. And this was very biased. I think there's lots of other fascinating areas, and maybe astronomy is even potentially the least impactful when you think about the solving the problems here on the planet. So that's always the problem for astronomers, how to be connected to solving the problems here on the planet. I do believe it is connected because I think it gives you this perspective. If you understand how unique our planet is and how insignificant many of our local quarrels are compared to this perspective. There's this famous quote from Carl Sagan about the pale blue dot that he made about there was this space probe Voyager taking the last image of Earth, where Earth is just a tiny little pixel left on the image. I think this kind of perspective also helps you solve the problems, but maybe more concrete problems. We have lots of problems in medicine, and we have lots of problems around energy. And so I think a lot of people work on computational biology and medicine, and this is really, it has been argued that machine learning is the sort of the mathematics that you need for biology, for complex systems. I think this is still a great area. Then there's this emerging area of materials and computing materials, simulating materials, discovering materials. I think that's also extremely promising because it's quite possible that in this space of materials we've only discovered a really small fraction. So there's a certain amount of materials that occur naturally. Then there's some materials that we have, often by chance, found ways to construct. And then there's also fascinating phenomena such as superconductivity, which we've discovered. And there might be many other strange phenomena out there that we just don't know yet. And many of these things might be extremely useful, for instance, when it comes to energy storage building efficient energy conversion tools, solar panels, carbon capture. All these problems can benefit from that. And maybe there's a second, I think, interesting trend or interesting direction for the future, which one could call computing with materials. Because if you think about quantum computing, I think it's not clear yet how useful this is going to be, and it's probably the wrong way to think of it as a replacement for a Turing computer or for a digital computer. Digital computers are very good at what they're doing, and maybe we're not doing quantum computation justice. So personally, I don't expect that it's going to change traditional computing so fast. But we have to think of it as a new component that's useful for certain things. And then if we think of it abstractly, what is computation anyway? Then I would think one way to think of it is it's a form of controlling dynamical systems. And the nice thing about digital computers is that in the end, these are then discrete systems, and you can analyze things in Boolean logics, and it's very simple. But if you have a quantum computer, it's running at different dynamics. You also want to control it. You want to be able to produce certain initial states, and you want to use this control and then run a time evolution to do a certain job for you. And it's probably going to be harder in certain things as our discrete dynamical systems, but it might be very useful when solving some of these problems, also the problems up here. So that's all I want to say about that, and I have, I don't know, 5 or 10 minutes left? Or? Yeah, okay, 10 minutes. So let me give you a few thoughts also on sort of more core theoretical algorithmic questions of machine learning. And you could call this part about some thoughts about the future of representational learning. So we've been thinking a lot about this also from the point of view of causality. Now, if you think about what is a representation anyway, so that's a classical picture from the early days of quantum mechanics. People developed, especially also here in the north, in the Nordic countries. I learned this morning at breakfast. We are not in Scandinavia, but we're in the Nordic country. So this was from another Nordic country in Denmark, where Niels Bohr and his co-workers developed this atom model. And this was a model that was supposed to explain the observed transitions, the energy lines in the spectrum, in terms of likening the setup of an atom to a planetary system, like with the sun and some planets orbiting around it. And this worked to a certain extent, but it also hit its limitations. And then other people in quantum mechanics, maybe the younger generation, people like Heisenberg, they said, well, it's useless to think of this in terms of planets and the sun, because it's a very different domain, and we should really not speculate about things that we cannot observe. So Heisenberg was saying, let's just focus on what we can observe, and let's try to find a mathematics or a model that relates the observable quantities to each other. And in his autobiography, he likens this to a positivism direction in philosophy, especially philosophy of science, which was popular around the time, especially in Vienna. And it's interesting, even if you can even somehow compare this to what we have in machine learning sometimes. You have this idea, especially in fields like ICA and also now in causal representation learning, that in the end there's a generative process, and the goal of learning is to identify the parameters of the true generative process. But if you think about it in terms of statistical learning theory, so you can have this view of learning theory that there's a teacher and the role, so there's a teacher network that generates the data, maybe adds a little bit of noise. And then there's the student network that tries to identify the true parameters of the teacher. And then you measure convergence of the learning process in terms of converging of the parameter vector to the truth. Now, according to Wapnick in statistical learning theory, this is exactly the wrong thing to do, because studying the convergence of these true parameters is a very strict requirement. Of course, if it takes place, it implies also convergence of risks, but not the other way around. So if you only study convergence of risks, you might get convergence of risks. So you might get the expected error could go to the lowest possible, realizable in your function class, without you having converged to the true function in any sense. So this is, yeah, maybe I'm talking too much about this. So that's one representation and some thoughts about connections to machine learning. Here's another example, which is actually, when I started working in the field, at the beginning I was working in neural networks and actually on spatial navigation and on, I think, what we would now call world models. It's more specifically cognitive maps. And cognitive maps, so this has been studied a lot in rodents. There's the idea, but also in humans by now, there's the idea that, so if you have an animal that wants to reach a certain goal, if it's always the same goal, then you could just sort of learn a mapping from what the animal sees to the actions the animal should take. But imagine you have to solve different goals or reach different goals. You don't want to learn a different model for all these different tasks. You want to learn one model that you can use for all the tasks, and that model then maybe could be called a map of the environment. And it turns out there's even some, in rodents you can find these so-called place cells that represent certain locations in the environment, or that fire up, or place neurons that fire up whenever you're in a certain area. So the question is whether we and other animals might have such representations in our heads. And maybe more generally, you could ask, so how should these representations look? You can even ask, what is a statistical representation? I mean, all the hype is around representation learning. I don't want to discuss this in detail now. You can ask, so clearly statistical representations, they contain information about statistical information, about mutual information, about dependencies, but they don't contain information about actions and the effect of actions. And this is a picture drawn by my wife that shows that sometimes an image could contain much more information than just what is where, but it could tell a whole story about what would happen to things if you were to intervene. So here you even there's several other agents in the image. Maybe you have some knowledge that this chicken might eat these things. You have some understanding of physics, what might happen to this system if this gets eaten, and you can picture the whole thing in your head. And this is close to. So this kind of simulation is something. If you wanted to support that, you need more than just a statistical representation. So you need something we could call an interventional representation. And here's the button again. So interventional representation is something that could include affordances of objects. So that's a term coined by psychologists. So an affordance means what kind of interaction might you be able to have with an object. What is a chair? A chair is an object that affords sitting on. It might look very different, but all chairs have this property that you can interact with them in a certain way, and maybe the representations should reflect that. And if you represent this object in your head, maybe you're already thinking about pressing this button. So it should be part of the representation. And I think it's connected to this philosophical problem, how the world gets into our heads. And maybe I'm not going to talk about that, but happy to discuss this in the break. So there's this fundamental problem. Our brain, whatever enters the brain from outside, there's a process of sensory transduction. It gets translated into neural spikes. Whatever is produced inside is also neural spikes. So it's all the same stuff, and nevertheless, somehow it gives us this illusion that there's a world out there. We can take things, we can interact with things. So this clearly, from a physiological point of view, this is a construction, and the amazing thing is that this construction seems to be consistent with the world. It allows us to survive. It even seems to be consistent across the individuals. We can talk about our mental models of things, and they seem to be not completely different. I think this is one of the fundamental problems of epistemology, and now it's starting to get within reach of what we can model. So I think this is quite fascinating to think about this problem. And I'm not going to read this, but there's a nice story from Brecht about a congress of philosophers discussing here in this monastery whether the world outside exists or not, or whether it's just in our heads. And then they decide to simplify the problem and say, does the Yellow River exist or not? But then while they're discussing it, there's a thaw in the mountains, the Yellow River washes away the monastery, so they couldn't decide finally whether the world really exists outside. So this points to one way of taking such model, that's the pragmatic criteria. So models have consequences. And maybe just very quickly, so 2 desiderata that I think causal representations should have. One is this idea of homomorphism. So there's certain structures in the world that have to be mapped to structures in your head. And I think the first example here is from Leibniz. He said, imagine that a living being is represented by number 2, and the concept of being rational, so endowed with reason, is represented by 3. Then, so Leibniz, the concept of human should be represented by the products F2 and 3. So certain logical structures in one domain are preserved in another domain, mapping them to integer multiplication. So that's maybe the first example of a homomorphism. And then there's the idea of consistency of a model. And here I'm quoting Hertz, who said that basically if I take an object in my hand, I take this microphone here, and I perceive it, and now I close my eyes and I move the microphone over, and I open my eyes again and perceive it again, then I'm not surprised. It should be in the same place. It should be in the place where my mental model tells me that it has moved to. So this kind of consistency the models should also have. And we're trying to put this, so we have various papers that study little aspects of this. We're trying to put this together to build causal models now. And I'm going to maybe skip this. We're trying to also connect this to modern representational learning. So here we have a paper where we have these additional objects that you can bind to certain representations, and then you can mix this kind of prompts with text prompts. So you can ask for it to put this Max Planck mark in different contexts, and the logo always changes a little bit according to the context automatically. And it's quite interesting. So this is the mark with Newton. Here we have it with Turing. It decided not to put a logo with Turing. And when we ask it to put the mark with Einstein, then it ends up putting Einstein's face on the mark. So somehow Einstein's face is such a powerful meme in the world that it even leaked on that. Okay, and then maybe as the last point, to connect it to what we're currently seeing. So I've been thinking already for a while that the big blank spot in machine learning is social and cultural learning. So we accumulate information across generations, we develop tools, beliefs, and practices that are too complex for any single individual to invent during their lifetime. That's the secret of the success of humans. There's a book by Henrich with this title. Now, this begs the question, what if we were able to train an AI model on a human, not just on input, output, or reinforcement, or label training data, etc., but on the collected cultural knowledge of humankind? Wait a second, we now have this kind of method, at least in as far as the cultural knowledge is written in text, and that's called a large language model. And you can ask whether this is a path to human-level AI. I think a lot of people believe that. I should say I very much don't believe that. And I cannot make this point now, but there's a lot of discussion, and so I've worked on this with Léon Boutou. We feel that a lot of the discussion is influenced by this mental imagery of science fiction, which already sort of pushes us into this AGI direction, because we can all fantasize about such kind of robots. So what we did is we used a completely different mental model from literature of Borges, to try to explain language models. And we proposed this notion, which we call the fiction machine. So there you imagine a library of all possible texts. There's a Borges story called the Library of Babel. So you have a library of all possible texts. You start printing a few words on a tape. And then the fiction machine, or the perfect language model, it simply finds all occurrences of these words anywhere in your library, and then randomly picks one of them and just reads the word that follows. And then it prints it and goes back to the first step. So that's a language model, and in a way you could argue that is what every language model currently is trying to do. Now this is a completely mechanistic thing. There's not much intelligence in this system, one could argue. And I like to compare it to this interesting story here. There's a guy called Nigel Richards. He was several times the world champion in Scrabble. He's from New Zealand. And I think at some point he must have gotten bored of being world champion. So he decided to compete in the French Scrabble championship. And he doesn't speak French. So he learned by heart the French Scrabble dictionary. I think he still doesn't speak French. And he became French Scrabble world champion. So I think this is the kind of intelligence that currently we see in large language models. So it's not about understanding. Of course, it gives us this illusion of understanding. It's about fluency, and it's about sort of regurgitating the narrative structure in the training sets. And we've started studying the causal reasoning abilities of these models and other things. So I have to conclude. I think there are two interesting instantiations of these causal representations. One is in data science. I think I don't really have the time to talk about this, but I think there's a very interesting space in between full mechanistic models of systems and pure correlational machine learning models. And that space is essentially causally structured models that have the freedom to model components using different kinds of methods. You model some of them using machine learning, some using simulations, etc. I think that's a very interesting way to think about these models. We have one paper that goes in this direction, but I think many more should follow. And the other instantiation is AI. Because you need models with interventions, because thinking in the end is acting in an imagined space. And let me just finish with one particular AI system. So this is from last week when we had the opening of the Ellis Institute, and we were watching a football match in my living room. And you can see Jan sitting here with our cat, and he started to be very friendly with the cat until the cat suddenly bit him. And interestingly, in his talk the next day, just found the slide yesterday, Jan was already talking about cats. So I think he's a very fast learner, and he concluded that any house cat can plan complex actions. So thank you very much. Yeah.
I just need to make a couple of quick announcements. Thank you so much, Professor Schölkopf. Get one more round of applause, please. So we still have about 15 minutes for a break now. Please leave this room unless you're in the robust machine learning workshop coming up. That will be in here. One important change of plan, the human-centric machine learning workshop is no longer across the street in the hotel. It is now downstairs in what they call the press room, but we've stuck a sign saying Eliel on it to reduce confusion. Also, if you have any problems finding any of the rooms for the session you want to attend, you can find us, the organizers and the volunteers. We have this orange necklace, lanyard. And enjoy the rest of the conference. Thank you.